Okay, so we studied derivatives for most of the first part of calculus, and um, we were interested in looking at the instantaneous rates of change and what led us to the ultimately discovering the derivative of a function, which is the collection of all those instantaneous rates of change, or the slopes of the tangent lines at those points. So we wanted to be able to figure out things like what was the instantaneous rate of change of a vehicle at a certain point in time, or we started out with as we did our secant line investigation, seeing how if you let the 2 points of a secant line get closer and closer together, they get closer and closer to the instantaneous rate of change at a certain point. So, and we used this modeling bacteria growth. So we wanted to know how many bacteria, or what was the growth rate of bacteria on a certain day, rather than over a certain interval. And so we can find that using derivatives, but that's only half the story. As you might imagine, we were able to take the derivative of a function, but there's got to be a way to go backwards, go the other way. So that is going to lead us into integral calculus, and we're going to look at integrals. And this describes how instantaneous rates of change, or instantaneous changes, accumulate over an interval to produce a function. So that's kind of going to lead us to our first thing, what is called the area under a curve. And in order to find the area under a curve, we're going to use an integral. There's two integrals, kind of branches off into two directions: indefinite integrals and definite integrals. Definite integrals work with a certain interval, so a defined slice of a function, rather than the indefinite integral, which would be most likely like the antiderivative. So if you take a derivative, you want to go back to the original function you had. You're going to look at the indefinite integral. So right now we're going to use and take a look at the area under a curve, and it is kind of just what it says, but it allows us to find some interesting things. So just going to pose a problem. A train moves along a track at a steady rate of 75 miles per hour from 7 a.m. to 9 a.m. What is the total distance traveled by the train? Okay, well, I've got this set up on a Inspire document, and so right here is our function, and the train is going 75 miles per hour. It's constant, doesn't change. So every hour it's gone 75 more miles. So we want to find out what's going on at from 7 to 9 a.m. And so our interval, what we would write, would say that we want to find the area under the curve from 7 to 9 a.m. Okay, so that's how we would write this interval down, and that's how it would appear to us in a book. It might also appear in a test or in a book as this. I'm using a mouse, that's why the numbers aren't that great. Okay, so either way it can show you the interval that you're looking at. So all that means is that we're looking from 7 to 9. And we can find this, how far the train traveled, we can find that easily. The train is going 75 miles an hour, doesn't change, over the course of 2 hours. So 75 times 2 gives us 150. So the train's gone 150 miles. That was pretty simple. But what that stems from is the area under a curve. So if we graph the velocity of this train, like we have right here on the Inspire, we see that it creates a rectangle here in this region. So we've got a rectangle right here. And if we find the area of that rectangle, if we find the area of that rectangle, we can find how far the train's gone, the accumulation of the instantaneous changes over a given interval, a period of time. So we notice that down our interval length is 2 hours. So I can get that easily. How do I know that? Well, it's from 7 to 9. If it were some more crazy numbers like 10.138 to 11.794, you could just subtract. So 9 minus 7 is 2. That's our interval. All right, the height of our rectangle is 75. Well, I know that because this line, this function, is always at 75. Now, I wanted to find the height at 9. I could have just done f of 9 and figured out the height of this rectangle, but I know that f of anything f of any x is 75. So I use my function to find out the height of my rectangle. So I get a rectangle, and I can just find the area of it. And I do notice that 75 times 2 is 150. So where that distance, rate, and time stems from is actually the area under a curve, the instantaneous, the accumulation, the addition of all those instantaneous changes. So that's a very basic example to illustrate what we're going to do. Let me show you back on the document here what we're going to look at. So let's say we had a function, and we wanted to find the area under the curve. Okay, that is obviously not a function that's going to produce a nice little rectangle for us. Okay, so if I tried to draw a rectangle, right, over to here to B, okay, and I wanted to find the area of that, notice that I would be grossly over-representing the area right here and under-representing the area right here. And while that over-representation and under-representation would sort of kind of play against each other, and I don't want to say cancel each other out, but some area I'm estimating in my rectangle here that shouldn't be there because it's not under my curve, right? And also here, this area is under the curve, but I'm not including it in my calculation if I just use this strict rectangle right here. So it's going to be an estimation, close, but not what we want. So that would only be if I used one solid rectangle. But as Archimedes and Newton and the other mathematicians of history looked at, they said, well, what if I broke that down into infinitely small rectangles? So the idea is that if we have a curve that describes the velocity or the change of some object, I'll try to recreate that. So what if we could split it into infinitely small rectangles? I'll just work with 2 this time. So if I split it into 2, let's start here. Say I go here, and then I start my second one here. Okay, so now I am, with one rectangle, I am a little bit under. Okay, and then I'm a little bit over here and here. But it looks like, visually it looks like there's about the same over and under. So that might be a closer approximation. The rectangles do a better job of approximating those. And how would I find those rectangles? Well, that's just, if I call this function f of x, and this is my interval, right? So my rectangle is going to be the height, which is just whatever f of x is at that point. So I could say, since this is one rectangle, my function would be the height, whatever f with b substituted into it is, and then whatever times whatever b minus a is. That's going to be the length of my rectangle, right there for this one. For here, the height of my rectangle, I'm going to have 2 heights. I'm going to have the height with a, and the height right here, split the difference between a and b. So I've created 2 rectangles. We'll get into the calculations a little later. And I'll do one more, just to sort of show how the more rectangles you have, the better your approximation is going to look. So we got one more. And you should be drawing these out along with the notes that you have. So let's draw 2 rectangles. So let's say I'm going to divide it into fourths. So I'm going to go here. And then I'm going to start from where this rectangle left off, touching just the tip of the function. Okay? And then every time I'm going to go back, this is called the left-hand rectangle approximation method. I'm going to get into what that means in the next video. So I'm starting at the left of my interval, so A, and then starting right here where this rectangle left off. And so where this rectangle leaves off, it touches the function here. So I'm going to make another rectangle, just jut straight out from it, and then about 3/4 of the way through. and then wherever this rectangle touches the function, I'm going to jut it straight out and make it end there. So now I made 4 rectangles. And notice that my margin of error is smaller. I'm a little bit under here. I'm a little over, and a little under. So I have smaller amounts of over and under. All right, and if I keep doing this, I'm going to get smaller and smaller and smaller amounts until eventually, if I make these rectangles small enough, they're going to be so small that the difference is almost negligible. You can't really even tell. And you'll be so close to that area under the curve, you'll be able to tell what number it's approaching. And approaching, that brings up the idea of limits. So we're not there yet. But this is so the area under a curve. What we're doing is trying to let rectangles approximate that area. And we'll do that with 3 methods, and we'll get to those next.